So I'm going to talk about Russian science and particle physics in the wake of February 24th. This is a little outline of and so one theme is going to be how historically there have sort of been two parallel science communities that developed, and we're sort of moving towards that again. I'll give you a little bit of personal history, somewhat shameless, and then I'll try to sort of chronicle the events of February 24th, and then the immediate reaction both within Russia and without Russia, particularly in the physics and particle physics community. And then I'll give sort of a summary. So let me start with this idea of two different physics and nuclear physics communities. So after the Second World War, there wasn't really what we call particle physics, which is the study of subatomic domain. There was really nuclear physics, the study of the nuclei of atoms, and that, of course, is what has led to the, unfortunately, destructive power of nuclear bombs. And parallel to that, there was sort of a basic research thrust, both in the US and also the Soviet Union. And one of those research thrusts involved taking very heavy nuclei and putting them in these particle accelerators and smashing them on each other. There were two large accelerators that were developed. One in Dubna, about 200 kilometers north of Moscow in the Soviet Union, and the other around Lawrence Berkeley Labs outside of Berkeley, California. And in those accelerators, as I said before, they would take atomic nuclei, smash them together, and for a very short time, they were actually able to synthesize, when those nuclei smashed together, they were actually able to synthesize artificially nuclei that otherwise would not be found in nature for a very short time, and they were subsequently added to the periodic table. This is one of those. This is actually the interior of the particle accelerator in Dubna. I've actually been inside that accelerator complex. So this is just a series of magnets that sort of confine and accelerate these nuclei and whip them up to very high energies, and then at the last minute they're smashed on top of each other. Now, as I said before, they use these to sort of synthesize these very heavy elements, even heavier than uranium. And this is a bit of a periodic table. So here's uranium. It's heavy. I mean, it has atomic. Doesn't matter. Atomic number 92. Atomic weight 235. It's just something that's heavy. These green elements are elements that are radioactive. They occur naturally. The things up here also can be found naturally. This element is lawrencium, named, of course, after Lawrence, Kansas. That's not really true. It's named after Lawrence, some dude out in Berkeley. But for the purpose of the talk, Lawrence, Kansas. Yeah. Everything in purple up here is something that was synthesized artificially. And because they had these two parallel experiments, two parallel facilities that were both synthesizing these heavy elements, each experimental group sort of took responsibility for giving it a name. And the names, in fact, did not coincide. So, for instance, these were some of the elements that were synthesized. They had an American name when they were initially produced, and the Russians gave them their own name. Kurchatov was one of the people that was fundamental to the initial Russian atomic energy and atomic explosive program. And ultimately, they were sort of arbitrated, and they have now standard names. Dubnium, of course, is named after it. They had to name Dubnium in parallel because they got lawrencium as a tribute to the American. So they had these sort of parallel names. These are called in science. These are called the trans fermionic wars, namely the elements that were beyond fermium that had these, there was sort of a war about what the naming convention should be, American versus Russian. At the Dubin Accelerator, they also produced what they call Moscovium. It's pretty obvious, but again, we have Laurentium, so we built them one better. Okay, so as I mentioned before, so that's an example of sort of the east-west schism in terms of nuclear physics. Now we go one scale deeper, and we're looking not at nuclei, but we're looking at subatomic particles, the things that make up the constituents of atomic nuclei. And I'm going to try and keep the physics to a minimum, but I'm going to indulge myself and mention one thing which, to my mind, is like the coolest thing ever. So I talked about particle accelerators. So particle physics is, as I said before, the domain of the very tiny, the particles that make up nuclei, protons, and neutrons, they're called quarks and gluons. Doesn't matter, it's an obscure James Joyce reference. And you do these studies by basically taking these accelerators and you smash particles, or you smash protons and neutrons together, and you see what comes out. Now you can also do that sort of physics by using not man-made particle accelerators, which you have to construct these big rings, or you can use something that occurs naturally. In our case, the particle accelerators that we're looking at are, for instance, supermassive black holes, or huge stellar explosions, things called gamma ray bursts, in which case the mass equivalent to the sun is vaporized in 1 second. You get these stellar explosions which will outshine the entire galaxy for 1 second. And they produce enormous light, and they also produce particles, not just light, but particles. So what we're trying to do in astroparticle physics is we're trying to do something like astronomy, but instead of measuring light, we're going to look at particles that are produced by something very distant, and in that way sort of, figure out something about the universe. Okay, so I talked about East versus West in the context of nuclear physics and these transfermionic wars. Let me give you another example of East versus West in the context of astrophysics. And here's where the astrophysics comes in. So the cosmic microwave background. How many of you have heard this term? A few of you. Oh, some of you. Okay, my wife, because she hears it every night. So that's not true. Maybe just once a week. So the cosmic microwave background is, to my mind, a very interesting phenomenon. So the human the human eye has light sensors in your eye that are about 100 billionths of a meter apart. And because of that, they're sensitive to radiation, to electromagnetic waves that are about 100 billionths of a meter long. As it turns out, that is the wavelength of light that comes from the sun. It's not an accident, of course. Our eyes basically evolved through evolution to match exactly the light that comes from the sun. It's obvious. Now, let's suppose instead of having light sensors in our eyes that were 100 billionths of a meter across, let's suppose they were 1,000 times bigger. In that case, what you would do is that you'd have to have some sort of an instrument that was a scale of 1,000 times larger. And of course, since there's a lot of big, ugly, unwieldy things in New Jersey, you would build something like this and you put it in New Jersey, and you would look up into the night sky. So now you're looking at wavelengths that are 1,000 times larger than the wavelength of light from the sun. So you wouldn't see the sun anymore. What would you see? You would see a picture that looks something like this, except it would be very faint. So you would look up into the sky, you see very, very long wavelength waves that would come from the center thing. That's actually the Milky Way producing very long wavelength light. And you'd look away from the Milky Way, and now everywhere you looked, in every direction, you would see this very long wavelength light. It would be everywhere. And in fact, it would be not only everywhere, but it would be dense. In every cubic centimeter of basically space, there are 400 of these long wavelength particles, that are left over from the Big Bang. This stuff over here is so-called background radiation from the Big Bang. It was produced 13.7 billion years ago, and it permeates the entire universe. And it was discovered, as I said before, when these two guys in New Jersey put together this instrument, which is capable of detecting something very long wavelength in New Jersey. It was the first time it was seen, 1965. And again, very quickly, people realized what they're looking at is basically the afterglow, the hum left over from the Big Bang. It was an enormous, I mean, to me, it's just a mind-blowing idea that we still see evidence right here from the Big Bang. Now, this was 1965, and very quickly, some people realized, and again, I apologize for the science, but I have to confess, I still remember the time I was sitting in a lecture hall. And it was like, maybe 15 people in this lecture hall in upstate New York. And there was some dude from some experiment in Utah, and he talked about this thing, and my jaw dropped. I thought, this is absolutely amazing. So after people realized that there was this cosmic microwave background radiation, they also realized that it had a very significant and tangible implication. Namely, that if you're trying to look at something that's going to produce particles at the very distant edge of the universe, for that particle to get to us, it has to be able to somehow penetrate through this omnipresent fog, this background radiation. And in fact, it gets more and more difficult to penetrate that fog as the energy of the particle being produced gets higher and higher. So if you want to see the most explosive things in the universe, they in fact will not get to you because they'll be absorbed by this omnipresent fog. And that means that if you look at all the energies, all the particles getting to you from all directions, there's going to be a cutoff. And they were able to predict what that cutoff was. That's basically the idea. And the main tagline is that it's called the GZK effect. The cosmic microwave background radiation was discovered in 1965. This effect was written down in journals in 1966 in the US and Soviet Union separately. It's called GZK because they were separately recognized by two distinct communities essentially at the same time. Only later did they realize they were explaining the same thing and it had to be unified to one name. So again, this is the idea. You have a very high energy proton. This unit, don't worry about it, 10 to the 20th electron volts. The engineers will recognize this, but it's just a unit of energy. And the idea is that before we can observe this high energy proton, it hits one of these cosmic microwave background radiation light particles, and it's lost to observation at the Earth. So as I said before, there were three people, standard dead white dudes, that basically realized this. You can figure out who the American is. That's Ken Greisen. He wrote this paper, End of the Cosmic Ray Spectrum, will absorb by cosmic and not be observed at Earth. These are the Russians, Zatsepin and Kuzmin. They had their own article in JTEP Letters in 1966. The important numbers, as I said before, here's that 10 to the 20th number where they predict the cutoff. And this number, I said there were about 400 of these particles per cubic centimeter. They misestimated as 550. But they got the basic numbers about right. They both realized the implications of this. Hopefully it makes sense on some level. Okay, and then that was 66, and then people went out and they said, well, let's measure the actual spectrum, and in fact, this is what they saw. So here's that 10 to the 20th number, and you see exactly what they predicted. So this was a remarkable verification both of this background as well as our understanding of how particles are produced. For this particular topic, the tagline here is that it's not the Greisen effect, and it's not the Zatsepin-Kuzmin effect, it's the GZK effect, because only after the fact did they realize that two independent groups had separately predicted exactly the same physical phenomenon. Okay, so as I said before, after World War II, two parallel and often isolated physics communities developed. It's partially mitigated by the internet, but post 224, we're sort of moving towards a separation as well. Now, one difference is that right now, Russian science is nowhere near as strong as Soviet science was after the war. One perhaps stark example of that, did anybody know what this picture is? Yeah, let's do it. So this is a picture of, this shows what should have been the sort of soft lunar landing site of the Luna 25 module at the end of August. This shows this, so you can see a before and an after. The two pictures look exactly the same except for this thing over here. That dimple is where the Luna 25 crash landed. It was something of an embarrassment for the Russian science program. The embarrassment was only exacerbated by the fact that a week later, the upstart Indians were able to actually fly a lunar probe around the lunar South Pole, which is actually something of an achievement because of the difficulty in communication at that point. So again, the situation right now is a little bit different compared to what it was after the war, where the Soviet science program was in a much stronger position. Okay, so here's a little bit of, Eric went through it, I'll give you a little bit of shameless personal history to sort of lead up to 224. In 1989, I kind of insinuated myself into a postdoc in Novosibirsk. I was mostly interested in understanding what Soviet rock and roll was about, and I thought that was the most obscure place to figure it out. In 2006, through some clerical error, I got a Fulbright Award with the research in Moscow. I was actually at Kuzmin's office. He had since left. I also worked with the Arctic and Antarctic Research Institute in St. Petersburg, and we had a project to map out what the surface features were for snow in Antarctica. Snow does not deposit itself uniformly, but it turns out that there are these ridges, and it turns out those ridges are important for our research. Another clerical error, I got a mega grant in 2013, and Erin and I spent 3 summers in Nifty, Moscow. They still haven't fired the same clerk, and I got a second Fulbright in 2016, again in collaboration with ARI. Between 2016 and 2022, I had this sort of odd relationship with MIFI. Our grant had concluded, but I was still working with students, graduate students there. I was still actually supervising the research. In fact, I continue to supervise the research of one of the students even today, which is something that I'm a little bit ambivalent about, but I'll leave that for later. And then, of course, February 24th happens, and at least within Russia, as far as I can tell, each rector of each university had some latitude in making their own statement, at least immediately. Maybe right now they've forced everybody to close ranks, but at least directly after the invasion, each president of each university could make their own statement about their particular take on the war. The rector of MIFI made the statement that he respected each faculty member's individual, at least this was immediately after the invasion, personal opinions on the war. The Moscow State rector was emphatically in favor of the war, which was quite well publicized. And soon after the invasion, through a combination of my own personal objection to the war, plus some official machination at the administrative level, my affiliation with MIFI was dropped. I got basically a termination notice. Okay, here is a view of Nifty. So there is Kashirskaya Chaussee. It's on the southwest side of Moscow. The apartment where Aaron and I lived with our kids was over here somewhere, and my office, which was sort of a total. I mean, the whole thing was something of a charade. This megagrant thing. I'll just give you one little. Well, no, I'll save it for later. But the whole thing was something of a charade. It's sort of what you would expect from Russian bureaucracy. My office for this grant in some field that I had absolutely no prior experience in whatsoever was over here. I had this big office, bigger than anybody else on the floor. I had this big door, and it said something like Vetushin, Uchoni, Dave Besson. I had this big door. It was padded, bigger door than anybody else, big office. And my fraction of time in that office was maybe 1%. I spent 3 summers there and did very little that was useful, for them at least. All right. Now, right after the invasion, probably as many of you know, there was this unified statement from about 160 university rectors. Events are unfolding in front of our eyes that concern every citizen of I have to confess, I wouldn't trust the translation, I did it myself. The recent decision of Russia intends to put an end to the 8-year Ukrainian resistance in the Donbass and achieve demilitarization and denazification of Ukraine, as well as defend ourselves from a growing external military threat. And to some extent, making this statement, I think, sort of forced the hand of a corresponding response from foreign universities as well as foreign academic institutions. So, getting back to particle physics, in the wake of that statement from the Russian rectors at CERN, which is also one of these big accelerator complexes, it's the biggest accelerator complex, in fact, in the world. Right now, it's located in Geneva, Switzerland. They came out with a policy statement, an initial version of policy statement on March 8th. That was later made official by a meeting of all the signatory nations in August 2022. Condemnation of the invasion. In August, there was a complete expulsion of all Russian scientists from CERN. There would be no cooperation with Russia or Belarus until further notice. One of the peculiarities about particle physics is that in order to build these huge experiments, so what's shown here, this is one of those tubes that carry particles around and around. There's another tube on the other side of this monstrous contraption, and those particles are accelerated and they collide in the interior, obscured interior here, and then you watch what flies out after they collide. And this whole thing is instrumentation, which is designed to tell you what's flying out from that collision and give you information about what sort of particles are coming out. Because these are such large enterprises, I mean, this is a $1 billion enterprise, typically each country will sign up for some piece of this hardware. And each country has, historically, some sort of a specialty. So the Italians typically will build silicon detectors. So this is the same basic, these are the same basic units that go into your smartphone, transistors, etc. The Italians will do very small microchip technology. The Russians, not having a microchip industry themselves, are very good at building big, heavy things. So they used to export steel. So the Russians, a lot of the stuff on the outside requires lots and lots of steel. And the Russians typically would sign up to build and construct the steel enclosures which sit around these large experiments. This experiment is called the compact muon solenoid experiment at CERN. And I don't know how they did this unilaterally, but somehow the CERN directorate unilaterally basically said, we're going to expel all the Russian and Belarusian scientists, and responsibility for upkeep of all your hardware is just going to be reassigned to other countries. Now, as it turns out, maintaining steel is not as intricate a process as maintaining microchips. So this was not an extremely arduous transition. But nevertheless, that's where things are. Everything had to. There was a lot of software that had to be upkept. All right, so this made headlines in Scientific American. It made headlines in the New York Times. It was quite a big event in particle physics, and it sort of set the tone for other scientific collaborations as well. One of the experiments that I'm on is called the Radio Neutrino Observatory in Greenland, where our experiment is and where I was in August. In early March, the directorate of our group, it's not a big group, maybe 100 physicists, maybe 12, 13, I guess you could say maybe 13 institutions. And this was the statement, there will be no contributions, no attendance of RNOG collaborators of any events within Russia, and that included online participation as well. All affiliations with Russian institutes had to be dropped. Now, this is sort of a subtlety, and I haven't mentioned this explicitly, but this is an important issue that people are grappling with. How do you assign institutional responsibility versus individual responsibility? So, you respect the fact that there are individual authors, but you specifically object to the idea of recognizing a collective institution as part of Russia as a whole. So, any Russian institution is dropped. Here's the author list before and after. See, it's a little shorter. It's shorter because it had 2 Russian institutes removed from the author list. I'll just mention that there's a group of experiments that collectively do what's called multi-messenger astronomy. All it means is that there's a group of different experiments using different techniques so that when one of these spectacular stellar explosions happens at the edge of the universe, one experiment that measures protons will notify another experiment that measures gamma rays, and notify another experiment that measures electrons and say, hey, you should all look directly in this direction in the sky right now because something explosive may be happening. And that's called the multi-messenger alert. And it used to comprise all of these experiments in the world. So they're all connected by about a 500 millisecond notification scheme. After the war, this gigaton volume detector in Lake Baikal, I won't talk about it in detail, but it's pretty cool. They basically put these photo sensors in the water of Lake Baikal, which is the deepest, cleanest water in the on the planet. GBD was dropped from this worldwide alert system. Okay, and then another experiment that I'm on, this is a true particle of physics experiment, is called the Bell experiment. So Bell consists of another accelerator tube, and they smash matter on antimatter. And I thought their response to the events of February 24th were particularly notable because they actually took a look at themselves. So what they did is they had a publication. So typically in a publication, there's authors, and each author has an institutional affiliation. What they did for a period of a month or so is that they dropped the institutional affiliation for all of the authors on the author list, independent of where they came from, in order to stress the non-nationality of science. And they were the only group to do this. And again, I think this is laudable because they actually thought about themselves and their own personal, their own personal role as scientists in a broader political context. So this is a proactive step. Statement of support for Ukrainian colleagues, and again, singling out and particularly noting the individuals. So that went up a page. Okay, so they were trying to note the or distinguish between the individual responsibility versus the collective responsibility. And again, this is sort of a fine line that individuals themselves try to somehow negotiate. All right. Now, the official Russian response to the CERN expulsion was, to my mind, also interesting. So this was the statement from the Ministry of Science and Education. Russia is a CERN member with significant participation in large-scale international projects at CERN. Our participation has been reduced. That's certainly true. However, we nevertheless have cause for optimism since Russia's participation is important for both Russia and CERN. This is not true. CERN will be able to carry on its science entirely without Russian support. CERN can go on without Russia. Russia needs CERN more than CERN needs Russia. This is also sort of deviating from the sort of standard line that economic and intellectual sanctions will make Russia stronger, because it's going to basically create this internal, force Russians to develop their own internal economy as well as intellectual infrastructure. All right. Of course, there's been ripple effects, migration of scientists. 10% of the IT intellectual infrastructure has been lost since February 2024. As an aside, Zelensky has, at least initially, came out against Western countries absorbing Russian scientists. They should stay in their own world until they change the national philosophy. There's been a coordinated effort to absorb Ukrainian scientists at European and U.S. institutions, including KU. I don't know if everybody, but at least our department got a letter, basically got an email, asking us, basically giving a list of Ukrainian scientists and asking if we could consider collaborating with them, and if so, money would be made available to have them work at KU. There was nobody in particle physics on that list, otherwise I certainly would. And all those frozen Russian assets that you may remember, the EU is considering redirecting some of those in order to support Russian science. That hasn't happened yet, but it's on the horizon. Okay, I'm going to skip this, but I will say that we did in fact fly a barbecue lighter around Antarctica, and there's a barbecue lighter in that little thing, and it's about to go up in the air. If you want, I can give you more details, but yeah. All right, so here's the summary. Russian science is increasingly isolated. Access to experimental hardware and high-tech stuff is increasingly difficult, but the access to a lot of U.S.-made chips has nevertheless continued to flow unabated. In fact, they've had 20% more of this hard raw material, particularly for weaponry, in 2022 versus 2021. It's coming mostly through China. Russian scientists are increasingly either diverted to the military sector or leaving Russia. There's a small diminishing fraction which is going into academia, but again, academia cannot absorb, all the people that are graduating. And basic research will continue to shrink, I think, in Russia. It's got to be. It's being squeezed by the military budget. There's nowhere else to go. Current Russian students abroad are caught in some sort of science purgatory. I'm not sure what happens to these people, but moving from just getting visas to go to Europe for current Russian students is a lot harder. I mean Russian students in America is considerably harder now than it was pre-224. So when these people get their degrees, I'm not sure, and their visas as students runs out. I'm not sure what happens to them. I have one student like that right now. Students that are still in Russia can now only attend Russian conferences. They cannot attend international conferences. That is a bit of, that makes things difficult insofar as they are not getting any exposure to people on the outside who might be potential voters in the future. Some bigger issues, of course, one thing that I think Western science institutions should make an effort to do is to ensure that the Ukrainian science sector will remain viable beyond the war. So it's essential that we retain continuity of the Ukrainian science sector through the period of the war. There's sort of been a diaspora of Ukrainian scientists, and of course it would be a tragedy if at the conclusion of the war the Ukrainian science sector was so eviscerated that it could no longer continue in the international context. The other question is, to what extent is the citizenry complicit in the actions of the government, including the U.S.? When the first, when people started first circulating these notes saying we should just drop all of Russian collaborators from the author lists, internally my first thought was, well, when the U.S. went out and invaded Iraq, nobody came out and said, oh, I'm going to drop Dave from this author list because, the U.S. is, maybe a little bit overbearing internationally. And, with the unpredictability of American politics, I myself am somewhat grateful that nobody's looked at me first as an American and decided, to sort of punish me personally, which I think a lot of people would have had the right to do. And maybe this will, I have this idealistic idea that maybe this will lead to more self-reflection among the science community in general. I'm glad that this has forced Western scientists to think about the global context. I do think it would be good if there'd be more self-reflection among the science community in general, particularly in terms of, what is it that we're doing fundamentally? Does anybody really care that we discovered the Higgs boson? Probably not. If you're going to think about science in the broader political context, I think it would be good to think about that also in the socio-political context. All right, that's it. Thanks for your attention. I hope it was.